Hi, this is Alex's World of Math, and um, today we're going to be talking about permutations. And so today we're going to go through some examples, and then we're going to derive the permutation formula for you to use for future reference. All right, so suppose there are 5 different color beads labeled B1, B2, all the way to B5. And say we wanted to create strings of 3 unique color beads to later connect into bracelets. How many ways are there possible for these strings to be made? That is how many ways to select 3 beads without repetition, and from 5 uniquely labeled beads where order matters. So the terminology is very important here. When it says order matters, that means you're gonna have 2, 1, and 1, 2. Say these are we're not this is not this problem, but say you had these two possibilities, um, then they're going to be counted differently. But if you said that order does not matter, then these two are going to be counted as um, one way. All right, so that's very important. If order matters, then you can switch it around, and that's all going to be counted as um, unique orderings. And notice that there's no repetition. So whatever you pick out, you're gonna have one less possibility. All right. So let's see. You have bead 1, bead 2, bead 3, 2, bead 3, bead 4, bead 5. And you wanted to create strings of 3 unique color beads to connect into bracelets. And so let's express this 3 unique color beads as quote unquote slots. And so slot 1, slot 2, and slot 3. And in each of these slots, what we're basically representing is the first spot of the 3 unique colored beads as a string. So this is like representing one string. And um what we're gonna do in this slot method is we're gonna find how many ways to pick the first bead for the string, how many ways to pick the second bead and the third bead, and we're gonna use the multiplication principle to find the total amount of ways, and that's gonna be our answer. And in this case, how many ways to um how many beads can we pick for the first one? Well, there's 5 options, right? We have 5 beads that we can pick, and so that's gonna be 5. But after we pick one of these, notice that it says we're picking and we're selecting without repetition. And so because we don't have repetition, one of these are going to be removed. So let's say a arbitrary bead is called B5. Uh, that's going to be removed. It doesn't have to be bead 5, but we're basically saying that B5 is arbitrary, so it can be any of these. Just one bead is going to be removed to put in slot 1, right? And after it's put in slot 1, there's only going to be 4 other beads left. And so you're gonna have 4 other choices left for the second slot. And after you pick another bead, say like another arbitrary bead is called B2, is going to be removed. And so now there's only 3 options left. So say this one is put in here, and this one's put in here. And so now we only have 3 options left to put on the third slot of the bead string. And so we only have 3 ways, and that last bead is going to be, say, an arbitrary B1 bead, and it's going to be placed in slot 3. And so now we have 5 options for the first one, 4 options for the second one, and 3 options for the third one. And notice that this works for any arbitrary pick. You have 5 ways to pick any beads for slot 1, and we're accounting for all the possible number of ways. We're not restricting this to like one possibility where we're picking B1, and then we're exploring how many options left. Because we're basically saying it could be arbitrary, right? These 5 is representing 5 different beads. 4 is representing any other 4 beads. And so the next thing to do is that we're going to apply the multiplication principle. And to do that, we need to make sure that they're pairwise independent from each other. Well, the first pick, we made sure that's 5 ways, and whichever arbitrary way that we pick, or whichever bead we pick, that won't affect the 4 other ways, right? Like it won't place any restrictions or any like it won't force the second pick to be anything else because we limit that to be 4, right? We already counted for that restriction. Like if we had 5 beats here and 5 beats in the second one, that's going to be not independent because we removed 1 beat, so that's going to be a restriction on the second one that there's only 4 left. And so if we already accounted for the restriction, then they're going to be independent now. And so you can pick any 5 beads and then any 4 beads after removing that 1 bead for slot 1. And then after that, for slot 3, you're gonna have 3 choices. You're gonna have you can be like basically pick any of the 3 beads for the slot 3, and that's not gonna be affected by any outcome for whichever bead you pick for 1 or 2. It doesn't matter. It won't affect the outcome, and therefore they are independent from each other. And so now you can just multiply them and you will get 60. So the answer is 60 ways. Let's try another example. Um, so in an animal shelter, you have N kittens, each with a unique tag numbered from 1 to N. You want to select K kittens and give each one a unique bow from a set of K distinct bows. How many ways can you choose and arrange the kittens such that each kitten receives a distinct bow? So again, the question terminology and the specific wordings really matter here. They're basically saying you have n distinct kittens because they're saying that each has a unique tag. So and they're saying that this is distinct. So you have a pool. Say you have like a pool of n kittens, and you want to select k kittens and give each one a unique bow. So that means you want to make them distinct, right? And so from this you want to pick k distinct distinct uh kittens uh into k distinct bows. And so yeah, from a set you want to give each bow from a set of k distinct bows. So you first select k kittens. They're going to be distinct because we selected from a distinct set. And then you want to um assign each one k distinct bows. All right. And so this is going to be similar to the last question. Why? Because all right, so the first selection you want to select k distinct kittens from this distinct set. And notice that this is gonna be like a order sequence that you want to select, right? An order sequence, why? Because each of these kittens that you select are gonna be distinct. And so what that ensures is that the order matters. You're going to be assigning distinct bows to these selected kittens. And so the order that you give these bows does matter because if you have like a unique, like if you have like like all different color bows, and then you gave the first kitten that you selected a black bow, and then the third kitten that you selected a blue bow. That's gonna be a different ordering than if you gave the first kitten the blue bow, and then the third kitten the black bow instead. And so that's gonna make sure that you're gonna have ordered sequences. And so that's gonna be the same thing um as the last question, right? You basically um you basically are selecting from n kittens. So let's use the slot method, right? You have 1, 2, 3 slots, 4 slots, and then dot 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 to n slots, right? And these are sorry, k slots, because you're placing n kittens into k spots or slots, whichever term you want to call it. I like to call it slots. And so you want to place these in here, and then you're gonna select you're gonna give the bows. So how many ways are there to select n kittens? Well, there's going to be um how many ways to select n kittens into k slots? Well, there's gonna be n ways to select the first one, right? You have n choices. And then the second slot, you're going to, and actually, it might be better, yeah. So in this case, the k's, these each individual spot, they represent the bows. So um, instead of having to find the number of ways of putting n kittens, um, so like finding the number of ways of k distinct kittens, selecting that from the set of n distinct kittens, and then finding how many ways to put the bows on the kittens that you selected. You can find how many ways to select k kittens and put them um, in slots of k bows. And so each of these slots represent bows. So you're basically saying how many ways to put each kitten into each bow. So bow 1, bow 2, bow 3, bow 4, and bow k. So the first bow, how many choices do you have? You have n kittens that you can pick from. But notice that in the second one, you have n minus 1 choices, right? The second bow only has n minus 1 kittens left that can be assigned to it, right? Because one kitten was already assigned to bow 1, and so you can't pick that. And in the third one, like a similar thing happens. You have two kittens already assigned to two bows, and so you cannot choose two kittens from the pile of n kittens, and so you only have n minus 2 choices. And indeed, this keeps on happening um, until k, where you have n minus k plus 1. Minus k plus 1 uh, number of kittens that can be selected to bow k. Why is that? Because we're following the trend, right? You're doing you're doing n minus whatever number plus 1. And so uh like how many bows? Yeah, the number of bows that it is. And so in this case, we have this multiplication that we can use. Uh and we can multiply them because by the multiplication principle, if they're pairwise independent, then we're good. And how do we know that they're all independent from each other? Well, we already counted for it, right? Just like the last example, each of these events, we have n ways that it doesn't matter which kitten you pick, you're going to have n minus 1 ways for the next one. And it doesn't matter which n minus 1, which kitten you pick from the n minus 1 kittens, that won't affect any other outcome. And so you can multiply these, you can have n times n minus 1 times n minus 2 times n minus 3 times dot 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 times n minus k plus 1. All right. And there's actually a better way to express this. Notice that I want you to notice that n factorial is equal to n times n minus 1 times n minus 2 times dot 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 times 2 times 1. And so how do we obtain this expression? Because we want you know, a explicit formula for it. We don't want like an open form expression. And so how do we convert this into open form? We can use the fact that this kind of follows the n factorial, right? There is going to be an n minus 1, n minus k plus 1 inside the n factorial because um, like in this dot dot dot, there's going to be some n minus k plus 1, and then n minus k, then n minus k minus 1, and then you're going to get to the 2 times 1. They're all going to be n factorial. Like if you had 6 factorial, give me 6 times 5 times 4 times 3 times 2 times 1. And so if you wanted to express the n factorial in the n minus k plus 1, say you're choosing say your k was like 3. Say you wanted to you know, only select k cannon 3 cannons and place 3 bows to them, and you had 6 cannons to choose from. So n is going to be 6, and then k is going to be 3. You're going to get up to 6 minus 3 plus 1, which is also just equal to 4, right? So you're going to get up to 4, so you want this. So this is going to be our answer. If it was, if n was equal to 6 and k was equal to 3. So notice that these are left out. So this answer is also equal to 6 factorial divided by 3 times 2 times 1, which is also equal to 6 factorial over 3 factorial, right? And so that gives us a very nice formula to formulate this general expression, where we know that if we add n minus k minus 1 dot 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 you know, 2 times 1, like it's gonna get it's gonna multiply by 1 less every single time until 2 times 1. Well, isn't like if this entire thing is equal to n factorial, like once we add this part, then we can set up an equation, right? We have n factorial is equal to our answer. Let's express this as p n minus k. So you have p n minus k. And then this part, well, what is n minus k times n minus k minus 1 times n minus k minus 2 times n minus k minus 3 times dot 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 times 2 times 1? Well, that's just n minus k factorial, right? And so now we can derive a final formula for our p and k that's going to be equal to n factorial. You divide this on both sides, minus k factorial. And you get that the final formula is n minus n factorial over n minus k factorial. And so indeed, this formula is for permutations, and this can also be this is yeah, this is known as permutations, and this works for any time you want to uh select k from you know, a set of 1 comma 2 comma dot 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 comma n, which this is distinct, by the way. Any set has distinct items, so all items are distinct uh without repetition, and you have order selection. So whichever k items that you choose from the set, they're going to be counted as ordered. So you're going to find how many ways to select this. That would correspond to this p of n comma k. And that definition can actually right here. You can also say another way. How many permutations are how many ways to arrange k items from a pool of n distinguishable or distinct items into an ordered sequence. And so if you said unordered, that's not going to be true because I told you that the ordering really matters. Because if it's unordered, then some sequences will be counted as the same, one sequence. And so it's going to be less than permutations, and that's going to be known as combinations, which we will go over next. But this is the correct wording for permutations. And yeah, this is the terminology that we discussed earlier. And it's going to be a formula. So yeah. Yeah. And let's try a last example using our formula. So you have 8 different books. You want to arrange 4 of them on shelves. How many ways can you arrange these 4 books? Well, you have 8 distinct books. So distinct. So we have a set of 8 distinct books. That matches our definition, right? That we want to we want to, or actually 3 requirements for permutations is that you're picking from a distinct set of n of n items, and you want to pick k items from that you're doing an unordered selection and you don't have repetition. And so if you don't have repetition, let's see, you want to arrange 4 of them on shelf. That also means that you want to pick 4 as k. So this is k, 8 is n. And if you're arranging 4 of them on a shelf, you can't have the same book be put 4 times, right? It's a book. You have 8 different books, so you can't have the same book be placed 4 times. And so that matches our without repetition requirement. And the last thing we want to see is if order matters. How many different ways can you arrange these 4 books? Well, you're arranging 4 books on a shelf. It matters which combination of books you order, even if they're the 4 books are the same books. Like you can like um two different ways that you can do it would, for example, be using 4 books and swapping like the middle 2 books. That would be counted as 2 different ways of selecting this. And so that does match our requirement. How do I know that they're going to be the same if like that this question wants you know order sequences of books? Well, they gave us that they're distinct books and how many different ways. They want different ways, not uh not like unordered, right? They want to see how many ways you can arrange these 4 books. How many ways can you switch them around? How many ways can you get new books and then place them in all different ordered orderings? So this is a permutation application. And so now we can use our formula p n minus a comma, I mean n comma k is equal to n factorial over n minus k factorial, which is just equal to 8 factorial over 8 minus 4 factorial. That's equal to 8 factorial over 4 factorial is equal to 8 times 7 times 6 times 5 times 4 factorial over 4 factorial, and these cancel out. You get 8 times 7 times 6 times 5. All right, and if you want, we could just do the math of it. You get the answer. And so we get that this is 1,000 680 ways. That's our formula. That's pretty cool. And if we wanted to use our permutation the other way of using slots, we also could. We want to place them into 4 slots on the shelf. And notice that these are orderings because each slot matters. And so you have 4 distinct slots that, yeah, all of these, spots or slots, they're distinct. So that's why it's a permutation and an order sequence. And so how many ways to pick, how many different books can you pick for the first slot? You have 8 different books, and you select one book for that first slot. You have 7 left for the second, you have 6 left for the third, and you have 5 left for the fourth. And this is going to be the same thing that we got right here. And so yeah, that's the answer. In the next video, we're going to do combinations. Stay tuned. Have a nice day.